Alright, welcome to another AQA A-level chemistry video. Today I'm going to be doing a video on the ionic product of water. This video is something really in the long term coming. I talked about this in previous videos where I was referring to water both being acting as a acid and as a base, and saying that it's its own topic within itself. It relates to how it has its own equilibrium constant, and how it can also be used to work out the you can form an, because it's an equilibrium constant, you can therefore form an equation, and there if you can use that equation, you can also rearrange that equation to work out the concentration of H plus and the concentration of hydroxide ions. The reason this topic is so important is because, well, we'll find out later on in later videos, it's very useful in telling you really how to work out the hydroxide concentration, which can be or the H plus concentration. If you have the hydroxide concentration, you can work out the H plus concentration. And this is more useful for when you have weak acids or weak bases. Strong acids, as I said in my previous video, when I talked about, I'll leave a link in the description to that video, I talked about how we can work out the H plus concentration, or we can work out the pH, because really, for a strong acid, the concentration of a strong acid is the same as the concentration of as the same as the H plus concentration, because strong acids, remember the definition of a strong acid fully dissociates all H plus ions in solution, theoretically, right? Strongly dissociates H plus ions in solution. Therefore, we can assume if you had HCl, 1 mole per dm cubed of HCl is equal to 1 mole per dm cubed of its H plus concentration in solution, because it's a strong acid, it fully dissociates. And then it's the same sort of principle with the other strong acids, if they may be diprotic or triprotic, and the same principle for weak bases. So for strong bases such as potassium hydroxide, but we're just talking about POH, really. But they just strongly dissociate OH minus in solution, right? But when we're talking about the reason why the ionic products of water and the topic that I'm going to get into is so important, because we can't make that same assumption when we're talking about acids or bases. But I'll talk about acids just as an example. We can't use that same examples for weak acids, but as I said, same applies to weak bases as well, because they don't fully dissociate H plus ions in solution. So we can't assume theoretically that we definitely can't assume theoretically that the concentration of your weak acid, is the same as the concentration of H plus in your solution. In comes the ionic product of water, and though this may be a basic topic, it's very good at telling us, as giving us information to now calculate our H plus concentration. If we already have the OH minus concentration, and as I said, we already have the H2O concentration. I'll get onto that sooner or later. And this is very important. I'm saying all this information because you may be thinking, why are you just talking about this random thing? Just get on with the video. But I'm saying all of this because this topic is very important in your understanding of how to answer questions for weak bases. I'm not for weak acids or weak bases, and working out the pH of weak acids and weak bases, because it gives you the fundamental elements to start answering the first mark, the second mark, the third mark of this question, and eventually the fourth, fifth, and sixth mark. Because it may not be obvious to people at first, because they don't think they have enough information, when in reality the question is giving you more than enough information. You just need to use your understanding of the ionic products of water. I'll now get into the video. So water is very slightly dissociated into its ions. Dissociation of water. So water is very slightly dissociates into its ions according to the following equation. As I said in the previous video, water if we're representing dissociation of water as an equilibrium, right? The equilibrium, it technically is. We have to show the equilibrium sign, to show that it's a reversible reaction. Technically, it is, but equilibrium is so far to the left, we describe it as very little dissociation. But if we dissociation of water, it can be H2O to form H3O plus a hydronium ion, as we said in a previous video, plus OH minus. But the one that you probably more easier to understand, remember, but again, this hydronium ion is technically how we represent H plus being released in a solution with water, right? But the one that you'd probably be more commonly understanding knowing is the one that's highlighted in red. H2O gets dissociated into H plus and an OH minus. But as I said, very little dissociation because equilibrium is far to the left. Any H plus or OH minus that's in your solution will react back again to form H2O. Now this is an equilibrium constant, right? If we can represent this equation as this equation of dissociation, as an equilibrium constant. Hence, if we were to write an equilibrium constant for the concentration, because remember this is the concentration of H plus in solution, concentration of hydroxide ions in solution, and technically the concentration of water. And we don't usually refer to concentration of water, but if you think about it, really your solution is a concentration of water, but it's just so much greater that we don't really consider it, right? So hence, if we were to write an equilibrium constant for the concentration of this equilibrium, we follow the concept of products over reactants. Think back to equilibrium constants. Treat Kc in this sense as K as Kw, right? In fact, you know what? I'll just write it as this. There's nothing wrong with me writing it as this. I'll write it as this, right? Something that you're more familiar with. Kc. Products over reactants, so H plus OH the concentration of H plus multiplied by the concentration of OH minus over the concentration of H2O. Now the reason why we write this as its own, because if it was just this, right, you say, why do we need to write its own equilibrium constant? As I said before, this wasn't Kc, it was Kw, right? You go back to where this was. I don't know why it does that. Anyway, this was Kw, right? Why is this on equilibrium constant? It's just a version of Kc. Now the ionic product of water, the equilibrium constant can be simplified because, as I said before, the concentration of water is pretty much constant. As I said in the previous video, and equilibrium is so far shifted to the left. Water only dissociates slightly, and that's the big concept that you need to understand in this topic, that water's unlikelihood of dissociation is useful to us when making calculations using Kw, and it allows us to form a Kw equation. Therefore it allows us to work out the H plus concentration and OH minus concentration by forming an equation. So water only dissociates slightly, so the concentration doesn't really change. We can then rewrite a new equation. Kw is equal to H3O plus times by OH minus, as that before there. It may also be written as Kw is equal to H plus times by OH minus. Now, essentially what I'm trying to say here, this is constant, doesn't change. We can then cancel that, because we can assume that the concentration of H plus, that essentially what I'm trying to say is here, the concentration of that ideally is equal to this. And you're thinking to yourself, but David, you just said that the concentration of H2O is so far to the left, is so great. What is actually happening in your solution is, when you have products in there, is that your concentration of H plus is equal, in a pure solution of water, your concentration of H plus is equal to the concentration of hydroxide ions. So we can assume that, and if that's the case, right, if that's the case, then surely then there's no point in writing H2O. Now, get rid of this Kc now. So if I was Kc as by itself, we'd get rid of this H2O. There's no need for it. Now we form something called Kw. Right? Kw is equal to H plus concentration times by OH minus. And because Kw is an equilibrium constant, it behaves the same way as other equilibrium constants, such as Kc. Behaves the same way. So it's important. This is important because this means that it has a temperature dependence. The hotter the water is, the more dissociation it will occur, right? So remember back in Kc, or most of these equilibrium constants, right? It's temperature dependent. So the higher your temperature, the more dissociation. Well, basically, they're the temperature dependent. I'm not going to go to other equilibrium constants because some of them are also to do with the way the reaction would go. So if it's an endothermic or exothermic reaction. But in this case here, for KW, we're talking about dissociation, right? So breakdown of water, dissociation of water is an endothermic reaction. It requires energy to go in to break the bonds between water molecule, between the oxygen and hydrogen, right? To break that OH bond. So the higher the temperature, the greater the rate of dissociation, and technically the greater your KW. Now, the uses of KW. KW can be used to calculate the concentration of hydroxide ions given the pH. It could also be used to work out the concentration of hydrogen ions as well. Hydroxide ions, we can work out the hydroxide ions of solution, our H plus concentration, and it just depends on the situation that we have. But hydroxide, if we have already the pH, remember I said in the previous video, if we already know the pH and we want to work out the H plus concentration, H plus is equal to 10 to the power of minus your pH. And therefore, if you have KW, as I said, I'll explain how we already have KW. KW is a constant. It's a specific value that you need to know for your exams. Very easy to remember. If you have that and you have your H plus concentration, rearrange your equation, you get your hydroxide solution, your concentration of OH minus or hydroxide ions in your solution, right? But at room temperature, right, it's just so happens that KW is around 1 times 10 to the power of minus 14. That's not as easy to see there. As the concentration of hydroxide ions must be equal to the concentration of as the concentration of hydroxide ions must be equal to the concentration of hydrogen ions for pure water, we know the concentration of both must be 1 times 10 to the power of minus 7. If the H plus concentration is 1 times 10 to the power of minus 7, then the pH is 7. I remember in my previous video, I kind of talked about this. In our previous video, I went back to this scale here. Here is because if we have 1 times 10 to the power of minus 14 in total, right, of both H plus concentration and OH minus concentration, the reason why water, pure water and blood isn't technically 7 exactly, I think it's slightly higher than that, slightly more alkaline. Correct me if anyone's there, but all I know is not exactly 7. It's roughly 7, close to 7, but it's not 7. But pure water is, and the reason why why that's the case is because you have the H plus concentration of water is 1 times 10 to the power of minus 7. But if you only considered that, it'll make it look like water is really acidic. No, pH of water is 1 times 10 to the power of minus 7. But the pOH, if you want to talk about pOH, right, which is, by the way, if I wanted the definition of pOH is kind of the same concept as pH, but just with the just with OH, right? The pOH of water is also 7 because we have an equal concentration of both H plus in solution and OH minus in solution. That's why water is considered neutral, because it has an equal concentration of its H plus concentration and its hydroxide concentration in solution, in that same solution, right? So as the concentration of hydroxide, the reason why it's 1 times 10 to the power of minus 14 is because if we look here, if this is 1 times 10 to the power of minus 7, and we're multiplying it also by 1 times 10 to the power of minus 7, mathematically you can see that will equal 1 times 10 to the power of minus 14. Remember, BidMass, we just multiply we multiply our indices. When you're multiplying two indices, when you have two indices together, you add them. If you're multiplying two indices, you're adding them realistically, right? So minus 7 plus minus 7 minus 14. So if I've already explained this part already regarding the H plus concentration. So if H plus is 1 times 10 to the power minus 7, then pH is 7. This is why we say a neutral solution has a pH of 7. A neutral solution is one with the same concentration of hydroxide ions and hydrogen ions. That's pretty basic and pretty easy to see there. So you need to understand that Kw is equal to 1 times 10 to the power of minus 14. I want you to pause and think about the units for this for Kw, right? So I'm going to pause the video now and try and think of a unit for Kw. Okay, I'm assuming that you've paused the video and tried to answer it, or maybe you've just continued playing the video and looked at me like a wally. Fair enough. It'll be, if we know that, again, same principles here. This is, remember when we're doing equilibrium constant normally, right? Any type of equilibrium constant, we look at the units, we can determine by just what we're multiplying it. This is concentration of H plus, that's in moles per dm cubed, right? The concentration of H plus is in moles per dm cubed. Multiplying also by moles per dm cubed. There's no division here because the concentration of water is constant, right? I.e., the concentration of water is so clear. It's so the concentration. Basically, what I'm okay, let me finish off one point at a time because I don't want to start jumping ahead of myself. But the concentration of water is just, if you multiply moles per dm cubed squared, right? Essentially what you have is this: moles per dm cubed squared, or moles squared dm to the power of minus 6. So that's moles squared dm to the power of minus 6. Now coming back to this point here, I think maybe I didn't just explain this point well. If we had it like this, what I said was true in terms of the fact that it's like this, right? If we had it represented like this, because the concentration of the equilibrium is so far shifted to the left, as in this example here, right? The concentration of water is so high. Technically, we represent it like this, right? But it will be, these values would be, theoretically, it's like this, but sorry, I've made a massive mistake here in saying that this is equal to it. That's right. If it was equal to it, then your numerator and your numerator and denominator would be completely the same. I made a massive mistake. What I meant to say is, I'm not bothered to go and change the video again because it's only a minor incident. But I assume if you've come up with this part of the video, this is so much greater than this. That's what I meant to say. I'm really sorry about that. I made a mistake there. Editing that and chopping that part out would be quite long for me. So yeah, but it's what I meant to say is that the concentration of H2O is so much greater than the H plus concentration and the OH minus concentration, right? These values would be so little. This value here and this value here would be so little, and it'd be difficult to measure. It's just unnecessarily long. We don't want to do that. We don't want to do that. So we just take this, because we know the concentration of water is pretty much constant every time for every reaction. We can neglect it and just say that for Kw, the part that we really care about is this: the H plus concentration is the Kw concentration. Kw is represented by H plus times by OH minus, and if we have a diprotic acid, then it will be 2H plus in solution. So it'll be 2H plus, or if it's a dibasic acid, so dibasic base that we're using, 2OH. Triprotic, say you get that idea, will be 3 times by H plus. But yeah, I want to clear that part up because I think I made a massive mistake in that part. Everything else I said that was correct. It's just that the H2O is not anywhere near equal to H plus times by OH minus. It's H2O is so much bigger than H plus and OH minus. Is that it would be so, the numbers on the numerators would be so negligible. It wouldn't be good to use them as values. So that's why that's why Kw is represented in that way. Now the uses of Kw. The Kw is a constant at specific temperature. This means that at a specific temperature, we can relate the H plus concentration to the concentration of OH minus. And if we know the pH of a solution, we can calculate the concentration of OH minus. Now, I've got an example here from Seneca that if we say we dissolve 1 mole of HCl into a liter of water, the concentration H plus will also be 1 mole per dm cubed. And we can rearrange this, the ion product equation from Kw is equal to 1 times 10 to the power minus 14, which is equal to H3O plus times by OH minus, and just rearrange that equation. And I've put it down here, but I'll put it in a, let me actually just sketch it out, because I don't like representing it like that. I like to draw what's going on. So they've given you, they're asking you they're asking you to work out the concentration of OH minus in a solution of 1 mole per dm cubed, 1 mole per dm cubed HCl. Now this is actually so much easier than, I mean, say so much easier, it's a bit more easier than the real thing, because in reality they want you to work out the concentration of HCl, and it wouldn't be as simple as 1 mole per dm cubed. But you guys should be able to know by now how to work out concentration from moles and volume. They give you the realistically you have to do an extra step of working out the concentration from your moles and your volume, and then you'd continue this process on. But they just kind of gone to this point here, which is fine. We're just doing this as an example here, right? So they want you to work out the OH minus concentration in a solution of 1 mole per dm cubed of HCl. Now, how are we going to work out, the reason why this Kw is important is to work out this, right? So I said that we know that the Kw, if we want to work out OH minus concentration, the first thing that comes to mind when we think about working out the concentration of OH minus is Kw. We know that Kw is equal to H plus multiplied by OH minus. Now we know the concentration of Kw. We know but we don't know the concentration of H plus. Now, first of all, I like to rearrange my equations just so I know what I'm trying to work out. So OH minus would be equal to Kw over the H plus concentration, right? We know what Kw is. We know Kw is a constant of 1 times 10 to the power minus 14, but we don't know the H plus concentration. Now, they told us that we have a solution of 1 mole per dm cubed of HCl. Now, remember what I said about strong acids? We know HCl is a strong acid. So therefore, we can assume that the concentration of HCl acid is equal to the concentration of H plus. Because it's a strong acid, it fully dissociates H plus ions in solution. It fully dissociates its H plus ions in solution. We can assume that the concentration of HCl is equal to the concentration of H plus. Therefore, we now have the concentration of H plus, and now we know that the concentration of HCl was 1 mole per dm cubed. Therefore, the concentration of H plus is also equal to 1 mole per dm cubed. Write it on another line. Don't do it on the same line, because I was just too lazy there. But now we know how to work out concentration of OH minus in solution is equal to 1 times 10 to the power of minus 14 over 1. And that's equal to 1 times 10 to the power of minus 14. And the units would be moles per dm cubed, because this is, remember, this is moles squared dm to the power of minus 6, or you could refer to it as moles per dm cubed squared. Sorry, I'll run out of space there. So moles per dm cubed squared over moles per dm cubed, which is the same as cancelling that out. We now just have normal moles per dm cubed. So now the concentration of OH minus is 1 times 10 to the power of minus 14 moles per dm cubed. And this is what we'd expect. Now, this is now the answer, but if you're ever unsure about whether or not my answer is correct or not, the first thing you think to yourself is, does that make sense? In a solution of acid, would we expect our concentration of, in a strong solution of acid, essentially, in a solution of strong acid, would we expect our OH minus concentration to be that low? Yes, you would. We know that, does this value make sense? Yes, because we know we have an acid, quite a high solution. By 1 mole per dm cubed is considered to be quite a high concentration. 1 mole per d, not the, it's not the craziest highest, but it's not like usually in a lab, whenever, if you look at your any equipment when you're doing an experiment in a lab, right, especially for schools, they have to make, it's one of the safety precautions in your, actually it's one of your safety precautions that you put in your lab report, that you use a low concentration of acid, so that there's a low risk of skin burn, right? You'll use 0.1 mole per dm cubed. So 1 mole per dm cubed, which is going to be 10 times that, right, is considerably higher. So would I expect to have 1 times 10 to the power minus 14 moles per dm cubed of hydroxide ion in solution of strong acid? Yes, because you know you have a strong acid that will fully dissociate H plus ions in solution, exactly 1 mole per dm cubed of H plus ions in solution. So the concentration of H plus ions will be much greater than the concentration of hydroxide ions in solution. Therefore, this makes sense, and that's what you should always be thinking about in your exam. If they ever ask you to work out the pH of something, and you realize that I have a base, I'm meant to have something that's very basic, and the pH that I've got is actually acidic, I've made a mistake. That's what you need to be thinking about in your exam. Or if I'm meant to have a H plus concentration, it's meant to be very, in this case, it's meant to be very high, and I got something low. Is that correct? So I'm meant to have a H plus concentration of something that's meant to be very high, and my OH minus concentration is very low. Does that make sense? Yes, it does, because we're expecting the H plus concentration to be high. We've worked it out. They told us to work it out. But in case of just double checking, have I made a mistake? That's what you should be thinking about. All right, that's the end of the video. I know I've probably talked too much, but I like to just, I don't know, lecture, I guess. And that's it. Hopefully the video was helpful.